From among them, the first theorem, which is known by the name Runge's theorem. It states that these are approximation theorems. We can remember them as approximation theorems also. Let us take K be a compact set. K be a compact set in the complex plane C. And if f is an analytic function, if f is an analytic function on an open set containing K, then there exists a sequence. There is a sequence of rational functions such that poles of each Rm, क्योंकि rational functions के at most poles होते हैं, Rm lie outside K. That means ये एक sequence है जिसका जो analytic है पूरे K पे, उसका कोई भी pole K के अंदर नहीं है, and this sequence converges uniformly to function f on this compact set K. So this is the Runge's theorem, which provides you with a approximation sequence that any analytic function on an open set in which you have a compact set, and on that compact set this function is a uniform limit of a sequence of rational functions, but we have to be, this sequence of rational functions can be chosen in such a way that no function has a pole in K. So we have a situation. We have a compact set. Let this be the compact set K. Then we have an open set which contains K. We have an open set. Let this open set be G, and f is analytic function on this G. Okay. Now K G open है, आपका K आपके पास कंपैक्ट सेट है, तो कोई भी पॉइंट आप K की बाउंड्री पे लोगे और G पे लोगे तो they are at a positive distance from each other. So because of this, what I can do, I can choose an open set within the open set G which contains K, but this is D, and but this is such that कि आपका फंक्शन f जो है इस सिर्फ D पर नहीं एनालिटिक, ये इसकी बाउंड्री पे भी एनालिटिक हो जाए. So this is the way. So what this is, I can choose for proof. I can make such a selection. Let D be an open set containing K such that f is analytic not only on D, but it is analytic on D union boundary of D, and further this D can be assumed to be a bounded, क्योंकि compact set है, bounded है, तो obviously it will contain in some, क्योंकि कोई भी compact set bounded होता है तो that bounded set can be put inside some disk as well. So disk is always a bounded, so that's the one thing you can always consider this D to be bounded set, so that I can take some assumption on the boundary of this domain D. Further, we assume that boundary of D is piecewise smooth, so that हमारे पास Cauchy integral formula applicable हो जाए यहाँ पर, ठीक है? So now we have function which is analytic on domain D, and it extends to be analytic on its boundary as well, and its boundary is piecewise smooth, so I can apply the Cauchy integral formula. So by Cauchy integral formula, what we have the value of the function at any point inside the domain D is given by 1 upon 2 pi I integral over the boundary of D f at some zeta minus z d zeta, where z is any point in domain D. Let this be denoted by 1. So now what I'm going to do now, I'm going to chop the boundary of D into small pieces. इसको छोटे छोटे curves में हमने काटना है, and let us see how I have to cut it. Let me choose a color which will, okay, let me choose the red one. So let me cut it into smaller pieces. और वो pieces इस तरीके से काटने हैं कि हर एक piece के around आपको एक disc ड्रा कर सको, so that we are able to draw a disc around each such piece, and so that that piece entirely lies inside that disc, and the disc do not intersect this K, or indeed the disc is at a positive distance from this K. We have to select in this way. So then I will cut another piece in such a way that I can cut it into so many pieces. और obviously क्योंकि आपकी ये कर्व है, फाइनाइट है, कंपैक्ट है, तो बाउंड्री कंपैक्ट है, तो you will be able to cut this into finitely many such pieces only, and let that each piece be denoted by gamma j, and the disk that I am trying in such a way that that disk lies at a positive distance from this compact set K. This is the positive distance. Let me depict this also. This distance from boundary of this disk is always positive. This is always positive. Okay, we have this situation, and let us take the disk radius of each this such a disk be denoted by this radius be denoted by Rj. This is Rj, and the gamma, don't get confused with it. And the center of each disk be denoted by Cj. Okay, so we are chopping this boundary into smaller pieces, and the condition is that each piece must lie inside a disk with center on the curve on the boundary, such that that disk lies at a positive distance from K that do not meet this K. So let us do what I did. We chop boundary of domain D up into a union of short curves each short curve, let me denote it by gamma j, such that each short curve gamma j is contained in a disk D, and let the disk has a center Cj and radius be Rj, and that disk that is at a positive distance from K, at positive distance from K. Obviously, it is a positive distance from K, then not even the boundaries of the two sets match with each other. So we have this situation. हमें इस तरीके से करना है जिथे is disk is at a positive distance from this. Now, what I can do, I can break this function because I have taken this delta D as a union of something. तो डेल्टा डी और ये डिसजॉइंट यूनियन है एक्सेप्ट एट के एंड पॉइंट्स पे ये आपके पीसेस मीट करते हैं कर्व्स के, तो आई कैन दिस इंटीग्रल गेट्स कन्वर्टेड इनटू दिस मेनी छोटे छोटे इंटीग्रल्स में और उनका सम हो जाएगा. तो हेंस आई कैन राइट this fz, which is by Cauchy integral formula, as 1 upon 2 pi I integral over boundary. And you see, boundary is nothing but boundary is union of all these j's, and these are finitely many j's, gamma j's, and this is f of z upon, sorry, f of zeta minus z d zeta, and from the property of integral, this gets converted into summation over j 1 upon 2 pi I integral over gamma j f of zeta upon zeta minus z d zeta, and let that each term in this sum be denoted by some function, and let me denote this by some function f sub j at z, where f j z, by I am denoting this function at 2 pi I integral over gamma j f of zeta upon z minus zeta d zeta. Okay, we have this situation. So f ultimately is a sum of some functions, and let us now study this function fj, what it is all about. Let us look at this function. Let me go back to the diagram and write fj here. Let me write fj. What is fj? Fjz is 1 upon 2 pi I, and it is our gamma j f of zeta upon zeta minus z d zeta. So what do you have now? Look at this function. Obviously, this function on gamma j, this function is not defined. This indeed it has singularities on gamma j, because gamma j zeta jab bhi gamma j se hoga to denominator mein you will have the proper, and this will not be defined quantity. So it has singularities, but outside this disk, जो भी डिस्क गामा जे को कंटेन करती है, लेट दैट डिस्क विद सेंटर सी जे एंड रेडियस आर जे, outside this disk this function is analytic, and you see, you can check it, you might have done it in previous semester कि इस तरह के इंटीग्रल जब भी होंगे तो गामा जे के बाहर सच इंटीग्रल से जो ये फंक्शन बनते हैं, these are always analytic and even they vanish at infinity. So if you do not have any background for this, and you should have indeed, you can see some of the exercises from your previous semester, or you can have the gambling book, you can see it from there. In very beginning में आपने इस तरह के functions को उसने prove किया होगा. So now what can I say, that this fj is an analytic function, and in particular each fj is analytic, and it is analytic outside this disk cj का. इन पर्टिकुलर क्योंकि ये डिस्क जो हम चूज कर रहे हैं तो दे आर डिसजॉइंट फ्रॉम के, तो इन पर्टिकुलर ईच fj is analytic on k as well. So let me write this in bracket for emphasizing. In particular fj is analytic at k. This is the situation. And also fj vanishes at infinity. Once you get to know that it vanishes at infinity, then it is clearly that this function is analytic at infinity also. और जब function analytic at infinity होता है तो let me finally write it this in this way. and that is what we have. Let me recollect it. What we have that for each j, this fj is analytic. For outside of this disk, तो इस disk का outside क्या होगा? Z minus Cj greater than Rj. ठीक है, greater than or equal to, but let's take it. It is. And what is this thing? This thing is a neighborhood of infinity, G. What is this thing? This outside of any disk is a neighborhood of infinity. This is a neighborhood of infinity. And this means that this function is analytic in a neighborhood of infinity, or at infinity. Infinity पे ये function defined नहीं है, infinity पे undefined नहीं है, infinity पे it vanishes, it takes the value 0 as you approach to infinity, and hence this implies that infinity becomes the isolated singularity of this fj. And now we can expand this function into Taylor series about infinity. But जब आप अबाउट इन्फिनिटी किसी फंक्शन को एक्सपेंड करते हैं टेलर सीरीज में, तो वहां पर पावर्स आपके पास पॉजिटिव नहीं आती हैं, वहां पावर्स आपके पास नेगेटिव आती हैं. तो देयरफॉर व्हाट आई कैन से दैट ईच fj is nothing but has a Laurent series expansion, has a Laurent series expansion in descending powers of z minus cj. And that Laurent series converges uniformly, and that converges uniformly for any, for on this set totally, on this outside of this disk. So we have this situation. Everything, this idea here comes, Laurent series in descending powers comes from the power series expansion of a function about infinity. Once you consider function at infinity, and क्योंकि infinity में सारा reverse हो जाता है, वहाँ principal part में आपके पास पॉजिटिव पावर्स आती हैं, whereas आपके पास अगर जब फाइनाइट पॉइंट पे एनालिटिसिटी डिस्कस करते हैं तो वहाँ फाइनाइट पॉइंट आपके पास कोई पोल होता है या कुछ होता है, तो वहाँ पर लॉरेंट सीरीज में प्रिंसिपल पार्ट में नेगेटिव पावर्स होती हैं. तो यहाँ पर इन्फिनिटी के लिए प्रिंसिपल पार्ट में पॉजिटिव पावर्स होती हैं और जो एनालिटिक पार्ट है वहाँ उससे नेगेटिव पावर्स हैं. तो सो क्योंकि ये आपके पास रिमूवेबल सिंगुलरिटी बन रही है, तो आपके पास जितनी भी पावर्स होंगी लॉरेंट सीरीज में वो सारी डिसेंडिंग पावर्स होंगी जी. तो दैट मीन्स व्हाट आई कैन से, I can write this fj as a Laurent series, that is fj at z has this form of expansion. कुछ constants होंगे a and let obviously j मैं इसलिए रख रहा हूँ क्योंकि j के साथ it might change. Our n can be anything, n can change from 0 to infinity or anything. I'm just taking n. तो powers descending होने की वजह से you can write it as z minus cj power n. Okay, and this is valid for z minus cj greater than rj. So what is this thing? You see, now you have on right hand side you have a series which is uniformly convergent, and the convergence of series comes from the convergence of the sequence of its partial sums. So let us see what are the partial sums of this series. Now this series is uniformly convergent, okay. So let us take without any, because it is a removable singularity, I can take it from n0 to infinity. It is uniformly convergent, and series की convergence अगर आपको definition you remember that when you say that it's uniformly convergent means that the sequence RMZ, where RMZ is defined as partial sum, let me take it to be n from 1 to m, a n j 1 upon z minus cj to power n. This sequence, this is a sequence of partial sums, converges uniformly. It converges uniformly to fj for z minus cj greater than rj. You have this situation. Okay. Now let us look at what this Rm is actually. See, Rm is a polynomial in z 1 upon z minus cj, and this polynomial जब powers negative हैं तो आप जब इसको LCM वगैरह करोगे तो you will get it as a quotient of two polynomials. So that means it is a rational function. Note that each Rm is a rational function. Rational function. So from here it follows that this fj is nothing but it is a uniform limit of rational functions. Thus, we conclude here that fj is a uniform limit of rational functions. So each such fj is a uniform limit of rational functions on this set z minus cj greater than rj. But since you see what you have fz is a finite sum of these such fj's. J equals to what I'm not sure whether j is 10, 20, but the only thing that I'm sure of is that these are finitely many j's. So the only thing is that I have to keep it as fj. Since we have this is a sum, and you see each in this sum, this is a finite sum, and each term is a uniform limit of a sequence of rational numbers, and this being a finite sum implies that this f is a uniform limit of rational functions. So it implies that f is a uniform limit of, आप उन सारे sequences का sum कर लीजिएगा, you will get the same thing, is a uniform limit of, क्योंकि sum of rational functions it will again remain a rational function, and that you will get a sequence of rational functions, and I can conclude that f is a uniform limit of rational functions, but on this set इंटरसेक्शन, क्योंकि ये सारे डिस्क्स जो हैं ये डिफरेंट हैं. अगर आप डायग्राम को देखें, लुक एट द डायग्राम, तो हम डिस्क के बाहर ले रहे हैं, वी आर टेकिंग इट आउटसाइड डिस्क. जब सीजे पे ले रहे हैं तो उसमें नेक्स्ट वाला पार्ट भी इंक्लूड हो रहा है, तो बेटर जब आप इंटरसेक्शन ले लेंगे इस सारे बाहर के, तो ही जाकर आपका एफ डिफाइंड होगा. ठीक है, बट हर एक इस डिस्क के हर डिस्क के कॉम्प्लीमेंट में के कंटेन करता है. तो इन पर्टिकुलर आपके पास जो भी इंटरसेक्शन ले लोगे आप, intersection over J of all these sets z minus cj greater than rj. So this function fz comes a uniform limit of rational functions on this set intersection, and you know this set contains the k, and since each z minus cj greater than rj contains k, hence it follows that क्योंकि इस intersection का subset है k, तो it follows that fz is uniform limit of what you say, uniform limit of rational functions. And now let me see the final thing, whether where do the poles of these rational functions lie. We have to have these rational functions so that the poles do not lie in K. So here is Rm, you see, this is Rm. You will get the combination of all such Rms to be the new sequence which converges to F. But इस Rm का पोल कहाँ है? इस Rm का पोल Cj है. तो Cj कहाँ लाई कर रहा है? Cj उस कर्व पे लाई कर रहा है. सीजे इस कर्व पे लाई कर रहा है और ये आर एम हम कंसिडर कर रहे हैं, दैट मीन्स इन पर्टिकुलर इसका पोल जो है के में नहीं है, क्योंकि दिस डिस्क इज एट अ पॉजिटिव डिस्टेंस फ्रॉम के और ये काफी दूर है आपके पास, तो दैट मीन्स किसी भी आर एम का पोल जो है वो के में नहीं है। तो इन पर्टिकुलर जो न्यू सीक्वेंस आप फॉर्म करोगे बाय टेकिंग सम ऑफ ऑल दीज रैशनल फंक्शंस करस्पॉन्डिंग टू ईच जे, तो नो रैशनल फंक्शन विल हैव पोल्स इन के, एंड दैट मीन्स I can conclude now that this is a sequence of rational functions having poles of k. So this is all about Runge's theorem. Do you have any query, anything to ask about this thing? बोलिए.
सर स्टेटमेंट रिपीट करना फिर से.
Okay, let's go to the statement. ये यहाँ स्टेटमेंट है आपके पास के जब आपके पास k कोई कॉम्पैक्ट सेट है, लेट मी गो टू द डायग्राम. It says that when you have a k as a compact set and you have a function f which is analytic on some open set, let that open set be G, then conclusion is that on k आपका फंक्शन ओपन सेट G पे एनालिटिक है और k G के अंदर है, तो फिर उस k के ऊपर आपके पास एक ये सीक्वेंस मिलेगी रैशनल फंक्शंस की, और उस सीक्वेंस के किसी भी फंक्शन का पोल के अंदर नहीं होगा और वो सीक्वेंस यूनिफॉर्मली कन्वर्ज करेगी फंक्शन एफ को इस कॉम्पैक्ट सेट के ऊपर. ये आपके पास रुंगेस थ्योरम का स्टेटमेंट है. इज इट ओके?
सर
तो ये बड़ा एक स्टैंडर्ड रिजल्ट बन जाता है अब आपके पास कि कोई भी एनालिटिक फंक्शन एक कॉम्पैक्ट सेट पे जब आप उसको रिस्ट्रिक्ट करते हैं, तो ऑब्वियसली एनालिटिक फंक्शन जब आप लेते हैं तो यू टेक ऑलवेज अ डोमेन. तो अगर उस डोमेन के अंदर जितने भी कॉम्पैक्ट सेट्स होंगे, तो देन on such compact sets that analytic function can be approximated by a sequence of rational functions, and none of the rational function will have a pole in that compact set k. So I'm going to finally state a shorter version of Runge's theorem, for which I'm not going to do the proof. We have to use only this part, and then I will conclude. There is a sharper version of Runge's theorem. So what is it? Let me write it in black. It says that let K be a compact set. K be a compact set, and compact set in complex plane C, and let us suppose that f is some analytic function. F is analytic function on an open set containing K, let S be a subset of the complement of K but in extended complex plane, इसमें infinity भी है, such that each component of C infinity minus K contains a point of S. So S is selected in such a way कि C infinity minus K के जब जितने भी components है तो S हर component को intersect करेगा. So this is the way. Then F can be approximated uniformly on K by rational functions with poles in S. So you can see the difference. It is the Runge's theorem, but it's a sharper version, or sharper version in this sense. The first thing is that, again, it's the same thing, that it's saying that you are having a sequence of rational functions and that converges uniformly on the complex set K to the function f, and none of the rational function has poles in K. But it says, it goes a step ahead in saying that we can choose that rational functions जिनका poles precisely उस set S में होंगे, and S has this description given that S is a subset of the complement of K in extended complex plane C infinity, such that each component of this complement of K has a points in S. That means that ये जो सीक्वेंस है आपके पास से फंक्शंस, रैशनल फंक्शंस की मिलेगी जो यूनिफॉर्मली एफ को कन्वर्ज करेगी, तो उस सीक्वेंस के पोल्स आपको, पोल्स की जो डिस्ट्रीब्यूशन है वो आपको के कंप्लीमेंट के हर के का जो कंप्लीमेंट है उसके हर कंपोनेंट में उसके पोल्स आपको मिलेंगे उस सीक्वेंस के. सो दिस टॉक्स मोर one step extra about the distribution of the poles of the sequence of rational functions that exists according to the Runge's theorem, which approximates uniformly this function f. So this is all that I have to talk about Runge's theorem. Next is a Mittag-Leffler theorem. We will do it in the next lecture.